So, the general form of equation of motion that we have obtained is given as rho du dt to rho f I and divergence of the stress tensor the divergence in the direction of the normal to the plane on which the stress is acting. That is, the divergence is with respect to the j component. Now, to proceed further with this equation, obviously we have to know something more about the stress tensor. Now, to look to the stress tensor, that what this stress tensor is likely to be, first of all think about that what this stress is. This stress is a reaction of two adjacent fluid elements, mutual reaction of two adjacent fluid elements, and represents momentum flux across the interface of two adjacent elements. The momentum flux across the adjacent part of the two elements, across the surface of the two adjacent elements. Now, obviously, this is a local behavior. So, we can expect that some local description of the fluid or the state of the fluid will perhaps be related with this stress. At least when the fluid is at rest, we have already seen that this stress is given simply by the local pressure. When the fluid is at rest, we have already seen that the stress can only be a compressive stress, which we have called the pressure, and it so happens that that is the pressure defined as in thermodynamics, considering mechanical equilibrium, thermal and mechanical equilibrium. Now, when the fluid is in motion, obviously, we cannot expect that it will be the same, because the momentum fluxes is likely to be influenced by the fluid motion. When the fluid is at rest, the momentum transfer across any surface is just by simple the molecular motion, but in this case we have another motion, the motion of the bulk material. So, the stress is unexpected to be the same as the stress at rest. Also, while discussing about the stress on in a fluid at rest, we saw that the pressure is the only stress and the pressure is also equal in all direction. That is, only the normal stress exists and it is independent of the direction of the normal. Whatever the direction of the normal is, the stress will remain the same, which is known as the pressure is same in all direction when the fluid is at rest. Now, when the fluid is in motion, we cannot expect that only the normal stress will act and also that the normal stress will be independent of the direction of the normal. Eventually, none is true. When the fluid is in motion, the stress is not only normal stress, and the normal stress that is present, that is also not same in all direction. I mean, if the direction of the normal change, the normal stress also changes. These are of course observation. So, we do not have that simple thermodynamic concept of pressure when the fluid is in motion. However, still when the fluid is in motion, still that compressive effect of the pressure or something equivalent to that is still present. So, we can try to redefine or get some quantity which is equivalent to or analogous to that pressure, which may not be pressure, but which is analogous to pressure, and then we can call it pressure, or rather that is what is the practice followed. In a when the fluid is in motion, we define such a normal stress which is the average of the 3 normal stresses considering any particular set of x's. Of course, this is a tensor property, we have already mentioned about it, that the sum of the diagonal, which is called the trace of a tensor, is an invariant. That means, if we change our axis system, the elements of the tensor will change, but the change will always be such that the sum of the diagonal will always be constant. And eventually, when the fluid was at rest, that 1/3 of that trace or the sum of the diagonal, that is what was the pressure. In this case also, there will be an 1/3 of that trace when the fluid is in motion, that stress tensor is also have a invariant trace, that is sum of the diagonal, and 1/3 of that we will call it again a pressure. 1/3 of the sum of that diagonal terms, we will call it again the pressure, but you should remember that this is not the same as it was when the fluid was at rest. The magnitude may vary, however, the basic concept itself is different. When the fluid was at rest, this 1/3 of the sum of the diagonal element is independent of the direction of the normal. Whatever is the direction of the normal, it will remain the same, but when the fluid is in motion, it is not so. It is not so. It depends on the direction of the normal, and even it can be shown that this 1/3 of the sum of the diagonal will be same if we take an average over all possible direction of the normal. If we take the average of the if we take the average over all possible direction of the normal component of the stress, that will also be the same as the 1/3 of the trace or 1/3 of the sum of the diagonals. We can also define it as the average of the normal stresses acting on a say small spherical element centered about the point at which we are interested. So, this quantity, this average of the 1/3 or 1/3 of the average of the normal stress, we will continue to call it pressure, but this subtle difference that this is not the pressure in thermodynamical sense, it is just basically a mechanical definition, and there might be, of course, might not be some difference with the pressure. What we call the pressure or what is the thermodynamic concept behind pressure is not the same as the 1/3 of the diagonal sum of the diagonal elements of the stress in a fluid at motion, but we will continue to call it pressure, but now meaning that it is simply the 1/3 of the sum of the normal stresses, sign reversed, the sign reversed, but it is not the pressure as we define in thermodynamics. So, with that, so we remember this 1/3 of sum of the normal stresses with sign reversed If you just look superficially as a mathematically, you will say that okay, in case of fluid at rest, again this pressure was defined as 1/3 of the sum of those diagonal elements or sum of the normal stresses with sign reversed, and we are defining the pressure here also with that. Okay, that is the similarity, but the main difference is behind the concept. The pressure is basically a thermodynamical quantity and is defined in thermodynamics. I think you have done little bit of it in your kinetic theory of gases and that is the same pressure when the fluid is at rest, but when the fluid is in motion, this 1/3 of the normal stress or some of these normal stresses is not the same quantity. But because of this mathematical similarity, we will continue to call it pressure, and quite often we will even forget this distinction. But remember that there is a very important conceptual distinction between the pressure in as defined in fluid at rest and as defined in fluid in motion. Okay, now then the stress tensor at in fluid at motion can now be written as this pressure plus some other part of stress which depends only because of the motion, because this is in when the fluid is at rest, this is the only stress, but when the fluid is not in rest, fluid is in motion, even the tangential stresses will be there, and even some remaining normal stresses will be also there, because this is the sum of the average. Each of the normal stress element, that is sigma 1 1, sigma 2 2, sigma 3 3, none of them are equal to this. So, little amount of or some amount of normal stress is left out. So, the stress tensor including these remaining part of the normal stresses and the entire tangential stresses is not included here. So, the complete stress tensor now can be written as say sigma I j as minus P delta I j plus we will call it d I j. This d I j is commonly called as the deviatoric stress tensor. When the fluid is at rest, this d I j vanishes and this mechanical pressure changes to that thermodynamical pressure or static pressure. So, when the fluid is at rest, Now, then we will see how to get little more about this deviatoric stress tensor Dij. The deviatoric name is because of the deviation. Okay, it is the deviation in the stress because of the fluid in motion. Now, as we said that what is this stress? Isn't this stress represented by this deviatoric stress Dij is basically the momentum transfer or sorry momentum flux across a material surface element because of the relative motion of the fluid about that surface. And from observation it is known that when fluid is at rest, this part of the stress does not exist, and also if the fluid is in uniform motion, that nowhere the velocity is changing, everywhere the velocity is constant, then also this stress does not exist. So, it can be concluded that this deviatoric stress comes because of non-uniformity in velocity distribution or because of velocity gradient. When there is no velocity gradient, there is no deviatoric stress. So, we can further take it, or you can say we can further assume that it depends only on then the velocity gradient alone, nothing else. This is just an assumption. However, even that is not sufficient to state something about this stress, because we must know then it may depend only on the velocity gradient. Then how? How does it depend on the velocity gradient? We make the simplest assumption that this deviatoric stress depends on the velocity gradient linearly. Eventually, for most common fluids, this assumption is quite good enough, and eventually those fluids which obeys this type of behavior or which have shows this type of behavior, that the stress tensor or the particularly the deviatoric stress tensor varies linearly with velocity gradient, are called Newtonian fluids. Now, if we try to write that relation mathematically, the velocity gradient is of course again there are 3 component of velocity in 3 direction. Each component can have gradient in all 3 directions. So, there are 9 components of velocity gradients. So, velocity gradient is also a tensor, which of course we have discussed earlier. So, there is a linear relationship between 2 second order tensors. How do we write it mathematically? The mathematical relationship for 2 scalar quantity, the mathematical relationship is straightforward. If y is linearly proportional to say x and x alone, you can write that y equal to k x, or k is a constant. But if we just have a simple constant like that, then you see that a particular component will depend only on one particular velocity gradient, not the other velocity gradient. If we write dij equal to k into duy dxj, this we write that a into duy or say make it k duk dxl, and this linear relationship will given by this a I j k l, a 4th order tensor. So, that any particular stress component may depend on all 9 velocity gradient components. A linear relationship between 2 second order tensor is not that one particular say stress component, let us say the component 1 2 will depend only on the velocity gradient 1 2. No, that d 1 2 will depend only on du1 dx2, that is not true. A particular stress component, say as an example d12, will depend on all the 9 velocity gradient linearly, and this is what that mathematical relationship d I j equal to a I j k l d u k d x l, where a I j k l is a 4th order tensor, and of course, it will depend on the properties or the behavior of the fluid, even the state of the fluid. What at this stage we can say that d I j, we know that sigma I j is a symmetric tensor, that we have already derived earlier, that the stress tensor is a symmetric tensor. Since sigma I j, the stress tensor is symmetric, d I j is also symmetric, because the other part minus p delta I j is just a diagonal or a constant term. So, the d I j is still symmetric, and since d I j is symmetric, this a I j k l must be symmetric in I j. I j k l has 4 indices I j k l. What we can say is that it will be symmetric with respect to these indices I and j. No, we can't say anything about k and l. So, you can write that since sigma I j is symmetric, so is d I j, and this gives a I j k l is symmetric in I and j. That is, we can interchange I and j. As an example, if A12 K L is same as A21 K L, which you can write A I j k l is same as A j I k l. Now, if you remember, earlier we wrote this velocity gradient tensor as sum of 2 tensors, one symmetric, one antisymmetric. You may look back, earlier we wrote it that d u k d x l is half of, if you remember this d u k, from where we did so many things. Which you remember we wrote that this is, we called the rate of strain tensor E k l, and this is the antisymmetric part, we wrote xi k l, and then we showed that this is E k l minus half epsilon k l m omega m, where omega m is that vorticity omega and epsilon k l m is that alternating tensor. To remind you once again that epsilon k l m is the alternating tensor and it takes the value 0 if k l m are not all different. If all of them are not different, epsilon k l m takes the value 0. When k l m is arranged in cyclic order, it takes the value 1. When it is not in cyclic order, then it is minus 1. Okay. Now, you substitute this in the relation for the Dybvig stress tensor. What do we get? D I j is A I j k l E k l sorry E k L minus half epsilon better to write Aij k L m first. Now, to simplify this further, we will make one more assumption, okay, and that assumption is we will consider the fluid to be isotropic. We will consider the fluid to be isotropic, that is, there is no direction preference, that is the stress acting on an element will be same irrespective of the orientation of the element, irrespective of the orientation of element. So, we will assume now, if we assume the fluid to be isotropic, the stress tensor will behave in that way, it will have no directional preference irrespective of the orientation, it will remain invariant, and that is possible if Aij k L is also a symmetric tensor, sorry, isotropic tensor. This will be possible if Aij k L is an isotropic tensor. So, this is the meaning of this assumption, that is why we have made this assumption, that the coefficient matrix Aij k L is an isotropic tensor. Now, before proceeding further, let us look at this way. Think about that there is only a vorticity. A motion is such that the velocity field is such that this E k L is identically 0. Just imagine that we have a situation, the velocity field is such that E k L is 0. Okay. Then d I g is given by the second term only, the vorticity term. Now, think that you change the direction of the vorticity. Vorticity is, as you have said, that it is 2 times the angular velocity. So, it is something like an angular rotational motion. Okay. So, you change the direction of the rotational motion. What will happen to d I j? Is all the elements of d I j will change its sign. Now, is it possible to have this type of thing in an isotropic fluid? Is it possible to have it in an isotropic fluid? Clearly no, it cannot, because changing the direction of the vorticity is equivalent that we have not changed the direction of the vorticity, but we have changed the orientation, of the element. We have not changed the vorticity, direction of the vorticity of the element, but we have changed the orientation of the element. Again we will get the same result. But an isotropic fluid, we have already mentioned that it is independent of the orientation, the stress will be independent of the orientation. So, it cannot, is not possible. What is the implication of that? What is the implication of this? That if there is a vorticity and we simply change the direction of the vorticity, the stress will, each element of the stress will change its sign, but which we say is not possible due to our assumption of isotropic fluid. In an isotropic fluid this cannot happen. Then what will happen? Yes, that is what it is, that the second term will have no influence on this dij, that is this term containing the vorticity will have no influence on dij, or this term will not be there at all. Vorticity has no contribution towards this stress, and I think it is also well known to you in case of a solid mechanics. If a body is in pure rotational motion, that body does not experience any stress. If a body is in pure rotational motion, it does not experience any stress, or rather rotational motion has no contribution towards stress. Anyway, we will also see it mathematically, but the mathematics now that will follow might be unfamiliar to you, but we will just take it for granted, of course, without doing any proof. We have from here we have obtained, this is of course a physical reasoning, that Aij_KL is an isotropic tensor for a fluid if the fluid is isotropic. By the way, to justify about this assumption that we have made an assumption of the fluid is isotropic, how far realistic this assumption is, whether it is totally absurd assumption? No. Most of the common fluids, or rather almost all the common fluids are nearly isotropic. So, this assumption is quite natural, rather it is not exactly an assumption, it is a fact. Of course, there are many fluids which are not isotropic, but the common fluids, and the example being air, water, they are isotropic. Okay, you can make water non-isotropic by making it some complex solution, but we are not interested in that sort of thing. So, as far as our cases are concerned, this isotropic behavior of the fluid is real, natural. So, this assumption is totally justified. Okay. Now, take it for granted, we will not study tensor theory here, but of course, it is an established proof in tensor theory that any isotropic tensor can be expressed, or isotropic higher order tensor can be expressed as a combination of the simplest second order isotropic tensor. This is a fourth order isotropic tensor. The tensor theory says that it can be expressed as a combination of second order isotropic tensor or any higher order, say fourth order, sixth order, fifth order, eighth order, whatever the order of tensor is, any isotropic tensor can be expressed as second order isotropic tensor. And the second order isotropic tensor is quite simple, or there is the very simple second order isotropic tensor, which is delta I j, the Kronecker delta, which takes the value 1 when I equal to j and 0 not. You can see that is the simplest possible tensor and it is isotropic. So, what says that any higher order isotropic tensor can be expressed in terms of delta tensor. This result, you just take it, accept it and take it for granted without any proof or anything, that all higher order isotropic tensor can be expressed in terms of simplest second order isotropic tensor. Okay, now then AIJKL so in this case combination we need two delta, product of 2 delta to give a fourth order tensor. Delta is a second order tensor, so we need 2 delta to give this a fourth order tensor. So, what are the different combination of 2 delta at a time? With these IJKL, we have 4 indices. How many combination we can have? See, we can have as an example delta IK, delta JL. Okay. These will be multiplied by some coefficients. Let us say we multiply this with the coefficient or say mu 0 plus say mu 1 delta IL delta JK plus mu 2 delta IJ delta KL. See, out of these 4 indices, these are the only possible combination taking 2 at a time. These 3 IKJL, ILJK, IJKL. We have no other possible combination. So, this is what is AIJKL. Now, see, we have already stated that the tensor AIJKL is symmetric in I and J. The tensor AIJKL is symmetric in I and J. And what is the result of that? If we apply it here, that it is symmetric in I and J, we can interchange I and J and K and L. What does it mean then? If we interchange I and J, look to the second hand side and what is the meaning of that, or what is the significance of that? Yes. See this, if we interchange I and J and K and L, this delta I K delta J L, this will become delta J K delta I L, which is the second one. So, if Aij has to be symmetric, in that case this mu 0 and mu 1 must be same. Yes, otherwise it will not, the Aij will not remain symmetric. So, we get that since Aijkl is symmetric in I and j, mu 0 must be same as mu 1 or mu 1 must be same as mu 0, whatever you, and we will call this to be mu. Instead of writing mu 0 and mu 1, we will just write it mu. Now, you see this what after this, what will be the significance of it, that this Aijkl now there is only one kl here, the last, and this delta kl is of course symmetric, it is only a diagonal matrix, diagonal tensor with diagonal element as 1. This then means that Aijkl is symmetric also in K and L. Because this right hand side is now symmetric in I and j as well as in K and L. So, the left hand side Aijkl also must be symmetric in K and L. Now, we can look to this, that second term containing the vorticity term, again mathematically. Look, this says Aijkl is symmetric in K and L, then it says that epsilon K L will also be symmetric in K and L. But we know that by definition that alternating tensor epsilon K L is not symmetric in K and L, but this needs that it must be symmetric. So, obviously, it cannot be present. So, mathematically also we get the same thing, that this second term cannot be present in the stress, or other way that vorticity will have no contribution in the stresses. So, now we can write what is Dij. Okay. Tell me what has now Dij? Dij equal to we need not write Aijkl now. Why write Aijkl again? Because we have already found what is Aijkl. We can write 2 mu delta ik delta jl plus mu 2 delta ij delta kl, and
So the term of omega drops out only in case of pure rotation or in general?
in general, because now we have not considered mathematically, we have seen that to see it easily we consider a pure rotation case, that when there is this term is not 0. Otherwise, if when both the terms have contribution, it is difficult to understand whether what is the contribution of individual. So, we consider an individual case to see that this is what it is, and after seeing that, okay, this result is general. In the mathematical case, of course, we did not consider it separately, it is a general case. Yes, no, how much it is? Okay, we want to write it full, 2 mu delta ik delta jl. No, there is E is also there, no? And plus mu 2 delta ij delta kl ekl. Okay. What is this? This is 2 mu E I j plus mu 2 d u k d x k delta I j. See, in these k l are repeated index. So, if you just make all these, if you go on writing the term for different values of k and l, of course, in 3 dimensional case k and l become 1, 2, 3, both k and l can be 1, 2, 3. So, if you carry out that product and the values of the delta are either 0 or 1, the result will be this, and same thing this will become this. Okay. This is now the deviatoric stress tensor. Now, we have expressed everything in terms of velocity. E I j is already expressed in terms of velocity. This mu is called the viscosity, coefficient of viscosity, sometime also called coefficient of dynamic viscosity, because there is another parameter which is mu by rho, mu divided by rho, which is also called viscosity, often called kinematic viscosity. To differentiate it, this is called dynamic viscosity, but its actual name is just viscosity, coefficient of viscosity. And the second one, mu 2, is called the coefficient of bulk viscosity, because you see this term present with this mu 2 is d u k d x k. Okay. What is that d u k d x k? It is divergence of the velocity or rate of expansion, this d u k d x k. Since it is associated with that volume expansion, this is called the second coefficient of viscosity or bulk viscosity. So, this is coefficient of viscosity, this is second coefficient of viscosity or coefficient of second viscosity or bulk viscosity. And now of course, we can put it in that general form of the equation. So, the equation of motion becomes rho d u y dt equal to rho f I plus d d x j of minus p delta I j plus 2 mu E I j plus mu 2 d u k d x k delta I j. Okay, before we proceed further, let me show you one more thing. A I j k L in general case, how many elements it will have? If you have 3 dimensional space, A I j k L is 3 3 3 3 81. Okay. So, the actual linear relationship needs 81 separate coefficient. Ultimately, you have landed into 2. Out of those 81, only 2 remains. All 17, rest of the 79 have become 0, vanished. How? Because of that isotropic assumption. Similar thing you have already done in your solid mechanics, where also you consider a stress strain. That is another difference in solid mechanics and fluid mechanics. The relationship is between stress and strain in case of solid mechanics. In case of fluid mechanics, the relationship is between stress and strain rate. And all the solids for which the stress strain relationship is linear, we call them elastic solids or Hooke's. They obey Hooke's law, that is the Hooke's law, also called Hookean solid, which obeys that linear law. We assumed similar thing here also, a linear relationship between stress and strain rate, just like as we do in case of elastic solids or Hooke's solids. We did same thing and we call them Newtonian fluids. Those fluids are called Newtonian fluids. In case of solid mechanics also, you ultimately needed only 2 coefficients, Young's modulus and bulk modulus. Here you are needing viscosity and bulk viscosity. Okay, now this equation can then again be written as rho d u y dt to rho f I. The first term can be taken out, that p term d d x j of p delta I j, d d x j of p delta I j makes it d p d x I. Now, let us once again go back to our deviatoric stress tensor. This is the general case. This equation is known as Navier-Stokes equations. of course, it is a vector equation for each component of momentum. I can take the value of 1, 2, 3, each will give one equation for each direction, momentum equation in 3 directions. So, there are 3 equations here, but once again let us go back to that d I j. What will be d I I? What will be d I I? That is sum of d 1 1 plus d 2 2 plus d 3 3. What it should be? If you remember that from sigma we have taken the sum of one average of the sum of the normal stresses as the mechanical pressure, which we have defined as pressure. Then what remains? We have taken out that isotropic part, then what remains of those sigma 1 1? Sigma 1 1 minus p is the d 1 1 now. Okay. So, what will be the sum of it? Sigma 1 1 minus p, that is sigma 1 1 plus p, sigma 2 2 plus p, sigma 3 3 plus p. That is what are the 3 diagonal terms now in d 1 1. So, sum of them what it is? Sigma 1 1 plus sigma 2 2 plus sigma 3 3 is 3 times p minus 3 times p. So, it is 0. Okay, we will continue it in the next class.